Simplifying a rational expression is a matter of combining two skills that we are already familiar with: the skill of simplifying a fraction and the skill of factoring a polynomial. Looking at our first rational expression here, we have x squared plus 7x plus 10 over x plus 2. There's a natural reaction on the part of mathematics students based on what you're already familiar with, that you're thinking that I see this 10 and this 2, and I want to simplify those two, and I see this x, and I want to simplify those two. However, we need to rewrite the polynomials as factors that can be simplified, not individual terms that can be simplified. So this route, written here in purple, is not going to work. That's not going to be an effective strategy for simplifying a rational expression. In order to simplify a rational expression, we need to factor both the numerator and denominator and cancel out any common terms, or common factors, excuse me. Our factorization of the numerator is x plus 2 times x plus 5. Our denominator is only one binomial already, nothing to factor, no common terms, no special patterns, so we leave the x plus 2 the way it is. We cross out these two as common factors, and we are left with the final result of x plus 5. Now you'll see on our lesson page that there's some consideration given to restrictions of the variable. Looking back at the original formula, or the original expression, we see this expression in the denominator, x plus 2. That x plus 2 being in the denominator means that x is not allowed to be negative 2. Despite the fact that the final version of the answer, in the final version of the rational expression, it looks like negative 2 would work. Because the rational expression was set up in this way, with that restriction being placed on it at the very beginning, it doesn't really matter what it looks like at the end. Yeah, we were able to cancel out that factor. We were able to divide out that common factor of x plus 2. But that's not going to help us when it comes to a restriction. A restriction is set at the beginning. So that x plus 2 from the very beginning means that x equals negative 2 is not a part of the domain for this expression. If it was a function, we would say it's not part of the domain. So while this is the simplified version, we understand that x is not allowed to be negative 2. And we're going to keep running into that issue as we go through these examples. Even if we don't mention it, you should assume that that issue is still there. You should give consideration to that denominator. Let's try another example. Here we have 4x squared minus 25 over 15 minus 6x. The top of the rational expression is a difference of squares, and we should factor it as such: 2x minus 5 and 2x plus 5. No special pattern in the denominator, but there is a greatest common factor in the denominator, which should always be our first look. We have a common factor of 3. Taking out the factor of 3 from the denominator, we're left with 5 minus 2x. You'll notice that there are no identical factors in the numerator and in the denominator, but we do have two factors that are opposites of one another. This factor right here and this factor right here are opposites. The 2x becomes negative 2x in the denominator. The negative 5 from the numerator becomes positive 5. Resist the temptation to try to call these two opposites. They are not opposites. The 2 is still positive. It's this factor from the numerator and this factor from the denominator that are opposites of one another. Both terms in the binomial have their sign changed. While we can't easily just cross those out, think about what it means to divide a number by its opposite. When you divide a number by its opposite, you don't get 1, you get negative 1. And that's the exact same thing that's going to happen here. We're going to knock both of those out, and it's going to leave us with an extra factor of negative 1. Writing out all of our pieces that still remain, we have the extra factor of negative 1. We have the leftover factor of 2x plus 5, and the extra factor of 3 in the denominator. Now you have other options in terms of how you want to write this. There are some who argue that because that 3 was by itself in the denominator, we should make that negative. That's not a common response. We typically don't see a negative number in the denominator. You also could run the minus sign through the whole numerator and change the sign of both of those, 2x and 5 if you'd like. Once that's done, because you have a monomial in the denominator, you could split it into two different terms and write it in what we would classically call slope-intercept form of a line. Now, this is not a perfect graph of a line. If we type this function in, if we type this expression in as a function, it would look like a line. But again, we go back to our consideration of the restriction. Way back here, we should have drawn the conclusion that x was not allowed to be 5/2. That's what would have made this factor right here equal to 0. Because x is not allowed to be 5/2, something is going to happen at that spot if we were to graph this polynomial. And as we move into future lessons, specifically lesson 6.3, that's what we're going to look at. What happens when we have a number that's quote unquote disqualified from the domain. One final example to look at in terms of the basics of factoring and dividing. We have a sum of cubes and a difference of squares, and we'll factor the numerator and denominator in those ways. So the numerator will match the sign, then we'll switch the sign, and in the denominator we'll have x minus 4 and x plus 4. Crossing out the common factor of x plus 4, we're left with x squared minus 4x plus 16 over x minus 4. If you happen to forget our rules for factoring a trinomial like this, remember that you still have, because of the way that this denominator is written, you still have synthetic division as an option to see if x minus 4 is a factor of that polynomial. Maybe you think you tried all the terms or all the possibilities for factoring that numerator. You're just not sure you got. Maybe you're not sure you got all of them. Maybe you want to make sure that you didn't miss a factor. Synthetic division is out there still as an option. Setting up the synthetic division for that denominator and going through the steps, we get a remainder of 16 telling us that x minus 4 is not a factor. So we're going to leave this as our final answer, but again, giving special consideration to the fact that x is not allowed to be 4 or negative 4. So what are our big takeaways from factoring rational expressions and simplifying them? Well, we want to make sure that we're always factoring our numerators and denominators. We want to make sure we're simplifying based on identical factors. In this example, it was x plus 2, and in this example, it was x plus 4. If we don't have identical factors, we want to look for opposites. So in this example, we had 2x minus 5 and 5 minus 2x. We looked for the opposites and we simplified those. But always in the back of our mind is this special consideration to what numbers is x restricted on? What numbers is our variable not allowed to be? That's not going to have as much of a big deal when we're just simplifying. But when we combine this simplifying together with the graphing work that we did in the previous lesson, those numbers are going to become very important and very noteworthy.